And hello, everyone. Um, I am Carlos Alberto Petri, having Rodolfo Jardim de Azevedo as advisor from Institute of Computing at Campinas State University, Brazil. I will present you our work named VirtFun Function Offload Methodology to Virtualize Environment. The agenda starts with the introduction and motivation, following to VirtFun methodology, experiments and results, ending with a conclusion. Cloud computing faces many challenges. We can highlight cost, privacy, reliability, portability, QoS, and performance as some of these challenges. To handle such challenge, cloud employ virtualization and computing resource in hardware, CPU, memory, storage, network, and software, things like configuration, deployment, management, orchestration. Virtual machines usage, VMs, grows over several domains like application ranging from scientific to commercial, and execution from HPC to embedded. With the increase in the adoption of VMs, higher overhead falls on the host in the cloud. This situation makes it possible to compromise the application requirement. Thus, the performance of VMs become a relevant issue for client and industries. To take the pressure, several approaches are considered. The academy and the industries have been using a variety of techniques, especially increase resource and distribute processing. Employ VM implies some assumptions. VMs relies on host resource, thus they depend on the performance of collocated host. Virtualization mechanisms imply lower performance of VMs. Thus, VMs are inherently slower. However, how can we improve the VM's performance? Currently, there are several techniques employed, but they are already in use. How to go beyond? We propose to use host research. Okay, it's already happens, but we propose use them in a different way. So, how to do this? Task performs better on host resources than VMs. VMs can take advantage of host acceleration skill as processing parallels accelerators. We can improve VM performance using these resources. Thus, VM can benefit from different host resources like CPU, GPU, FPGAs. So we propose the VirtFun, a novel methodology to offload the functions to run on the host. We define the function as a piece of the VM's application's code. The functions are outsourced from VM applications to host research, CPU, FPGA, and GPU. A requirement to execute a function is to collocation. The VM must be launched on the same host as the function is offloaded. Here, we will show you the layers considered in the infrastructure for VirtFun. The upper layer comprises the application layer. This layer represents the location where client applications on the VM are deployed. We depict it containing two clients with a pair of applications, each one. Clients can use any standard language and develop tools to make their applications. The second layer indicates the VM OS, in this case, two VMs, where each one runs applications of clients. At the bottom of this layer, you can see two pairs of shared memory areas, one for each VM. This area depicts the client-side data sharing. The third layer represents the hypervisor and host OS and several VirtFun support tools. As the primary tools, we highlight KVM, KIMU, libvirt, and Virtual FS. In addition, it has the vFunD, a task administrator that handles vFunctions from creation to deletions. The service that acts as an interface for data sharing among application and vFun research. Lastly, it has the necessary components to implement vFunctions in software or hardware. Now we are going to about four-phase VirtFun communication flow. In the first phase, negotiation, the client requests a vFunction to vFunD through a system call captured by the hypervisor. The vFunD checks the credential availability, slot, and register the vFunction to the application. Finally, the client gets the vFunD request result via another system call. In the second phase, activation, the client application invokes the vFunction activation, now registered via system call. The vFunD instantiates the vFunction, research, and launch the service interface. At the end, the client gets the vFunD activation results via another system call. In the third phase, computation, the client application extends data with the functionality with the function by means of shared area. The service provides the communication interface with the function on the host. In the last phase, release, the application requests the vFunction to be released via a system call captured by hypervisor. The vFunD checks the credential, availability, registration of the application's vFunction, and release it. Finally, the application obtains the result of release via another system call. The VirtFun data flow is composed by four components. Guest represents the client VM, where his application executes and exchanges data with the functions. Host comprises the host physical machine that receives data from clients and forwards it to the function. Out, in, correspond to data sharing channel that is a memory mapped files. This is an environment where packets containing data and metadata are transported between VM and host. vFunction denotes the piece of applications code offloaded to resources for both software and hardware. Here we start to introduce some details about implementation of methodology validation experiment. Both client and host side employ traditional development approaches and common tools. For client side, we highlight three pieces of application to exemplify, in this case in C language. A. Establishing the sharing. The application uses common open and mapping commands to establish two communication channels represented by out to the function and in from it. Once the channels are established, the application can exchange the data with the vFunction resource on the host via package. B. Sharing data. The package sent to the function out channel contains the application data and the command to be executed. To set command specifies that the application sends data to the function and the payload contains such data. The get command indicates that the application requests the vFunction result and the payload does not contain useful data. C. Receiving results. To get the result, the application needs to know when it is available. This is accomplished evaluating the offloaded computation state through in channel. After a get command, the application can obtain the result as soon as the stats become read. The package received from function in channel contains the application results and the stats of the execution. All developed codes use traditional language. For host side, we emphasize the main components and configurations for vFunction support. A. Managing vFunction request. vFun daemon makes all administrative tasks related to vFunction, such as register, launch, control, release, delete. The daemon handles guest system calls through hypervisor notification, the hypercall. B. Interfacing package transport. Service also uses common, open, and mapping command to establish two communication channels. It acts as a communication interface between the sharing and vFunction research. C. Sharing data. The data sharing is the basis for the communication between application and vFunction. It is a file system shared between guest and host, exported by the guest to the host, handled by the virtualized tool. This tool employs several mechanisms to carry out its work. Fuse is a file system protocol made available as a user space process, which implements an interface for virtualized device. DAX functionality avoid multiple I/O communications and data copy to and from host. The sandbox mechanism offers access restrictions to increase security. The mount namespace grants access only to the shared directory, not allowing it to escape from that directory. seccomp implements system calls restrictions, giving access only to registered calls. Sorry. Here I have the D, driving, and E, developing as I talk. Okay. We decided to fix the file hierarchy to standardize this and simplify the development. Define the /var/vfun path as a root starting point. Admin directory holds the vfund task admin daemon. Service keeps all application service pairs to interface with the corresponding function. VMCLI directory holds all data sharing hierarchy for clients. Each client has its own restricted root point, where several applications have their own area for data sharing. Experimental results. We conduct our validation experiment on hardware Intel Core i7, 16 GB of RAM, 480 GB SD storage, containing the software Ubuntu Server 20.04, kernel 5.4.0, with KVM support, QEMU 4250, virtualized, libvirt 630. For the experiment prototype, we selected two mathematical applications to execute, factorial and Fibonacci. We also established some definitions for the application's execution. Domain indicates a method for a combination of guest host execution, represented by host-host, guest-host, and guest-net. Instance represent a round of calculation composed by a combination of repetition and iteration. Time indicates the amount of time elapsed for the execution for one instance. Value, a number chosen as application parameter, defined as a high result considering 64 bits of data width. This table shows you the application's round analysis. For instance, until 10 iterations, the execution time remains virtually the same, considering all domains, approximately 16 seconds for factorial and 19 seconds for Fibonacci. This happens due to the system resource being able to properly handle the load of this instance. For instance, from 100 iterations, the time remains linear for the host-guest and guest-host domains. However, for guest-net domains, the time evolves in a nonlinear way, reaching over 4 times. This image show you the application's graphic analysis. In the first two sets of bars at leftmost, we can see that the 3 domains remain linear in execution time. Conversely, in the last 3 sets of bars, this does not happen anymore for the guest net domain. But for the first 2 domains, the time remains linear. Thus, our methodology demonstrates efficiency and scalability, make it viable to be employed as a mechanism for VM's speed up. Speaking of conclusion, we can say that we propose the VirtFun, a methodology to offload pieces of client applications code to host resource, the functions, as a non-invasive approach for developers using traditional language and tools. We made vFunction flexible, once both hardware devices and software programs can be used to offload application codes. We developed a prototype experiment to validate the effectiveness of our methodology. The prototype runs 2 applications to evaluate the robustness of the methodology. The experiment rounds employ several execution scenarios, varying vFunction, instances, and domains. The runtime of the VM application was virtually the same as those on the host. VirtFun achieved 4 times speedup comparing our methodology with the traditional network execution. In addition, the VirtFun performance is comparable to the host native execution. Finally, we demonstrated that VirtFun is an effective mechanism for accelerating VMs. As our future works, based on the promising results yielded, we consider integrate vFun with FPGAs, since this device have potential as function accelerator. We also consider to integrate the VirtFun as an additional resource in cloud computing. Thank you for your attention. I'm ahead for questions.